In this video, we want to consider the consequences of mismatch of p orbitals. We know that when we have a double bond, for example, between two carbon atoms, or maybe carbon and nitrogen, or carbon and oxygen, or a double bond between nitrogen and oxygen, the pi bond that is formed results from an overlap of the p orbitals, what we call the pi p orbitals, the ones that are perpendicular to the plane of the molecule. Of course, we've covered this in previous videos, but what we want to consider is, within these situations, all the p orbitals are from the same subshell. We have 2p orbital and a 2p orbital overlap. Now, what happens if we have, for example, carbon double bonded with sulfur, or maybe phosphorus with oxygen, or sulfur with oxygen? Actually, let's keep these consistent. Oxygen with phosphorus, oxygen maybe with sulfur, oxygen with silicon. In this situation, we would have 2p orbital overlapping with a 3p orbital. The 3p orbital, of course, is larger than the 2p orbital, so you have two things happening. You have some mismatch, so the overlapping is not as effective. Therefore, these double bonds, or the pi bonds in these systems, are considerably weaker than the pi bonds when you have an overlap between two p orbitals from the same subshell. 2p, 2p, this would be 2p, 3p from sulfur, phosphorus, silicon. These would be 2p, 3p overlap. And here we have a size mismatch, so the overlap is not as effective. So these pi bonds are considerably weaker than these pi bonds. Now, what happens if we, say, have 3p overlap? For example, try with sulfur, or with phosphorus. Now, the orbitals are the same size, but quantum mechanical calculations show that the greatest electron density in the 3p orbitals is right at the very tip. So these pi bonds will be even weaker. And we see consequences of that. For example, we have diatomic nitrogen, but typically not diatomic phosphorus. Instead, you have two single bonds, and these might link together to give us a whole polymer like that. Or we have oxygen molecules, but not typically sulfur molecules. Again, it's more likely to have a single bond on each side, and again, you can have a whole string of these. We have carbon dioxide, but you don't see, for example, typically silicon. dioxide. This you don't see. Instead, it's more likely to exist in this form, where here you have single bonds throughout, and again you can have a whole string of these connected together rather than having this structure. You can have ketones, carbonyl group with two organic groups attached to it. But now, if we put sulfur in here, this does not happen. Instead, what you are likely to see is single bond here and a single bond on this side. So again, you can have a bunch of these linking together. And again, it's all predicated upon the phenomenon that mismatch of pi orbitals makes for weak double bonds, or the pi bond is considerably weaker. So, or even if you don't have the mismatch, as for example trying to form a double bond with sulfur or phosphorus where you have overlap of 2,3 p orbitals, again the electron density is pretty much right at the tip of these, so even if you do have some overlap, you don't have very effective overlap. So these do not form as a general rule, nor do these, because now we have the mismatch of the pi orbitals weakening these pi bonds. So again, here now when you have 2p overlap, that's very effective. You can have a pi bond of a respectable strength. Again, that's why we can have dimolecular nitrogen, but not phosphorus. Instead, you have the single bond on each side, and you can form a whole polymer, or a whole string of these can be linked up. Same thing for sulfur. Typically, it doesn't exist like this. You're going to see it in this form. We can have carbon dioxide, but not usually silicon dioxide. You're much more likely to see it in this form. This again is the mismatch of the pi orbitals here. This would be 3p overlap, but that's very ineffective. Same thing here. Here we would have mismatch of pi orbitals, so instead of having the double bond here, it's two single bonds for sulfur, and again you can have another linkage of these compounds. Whereas if you have oxygen, then you can have the carbonyl with the double bond with the pi bond present. So this is a simple introduction to the consequences of mismatch of pi orbitals, 2p and 3p orbitals mismatch, or, for example, with these two compounds that really don't exist, you'd have 3p with no mismatch, but again, because the electron density is mainly at the tip of the orbitals, even though you do have some overlap, it is not an effective overlap. So those are just simple demonstrations of the results of ineffective 3p overlapping of the p or the pi orbitals, mismatching of 2p, 3p pi orbitals. These are perfectly fine, so these double bonds are fairly strong. In the next two videos, we will show how the concept of mismatched orbitals has very important consequences in biological systems and biochemistry, and we will have 2 examples of that in the next 2 videos. Again, a reminder that the playlist for all the videos is at the website digital-university.org.